welcome to all to the presentation on Kalina cycle. So far, we finished the two uh, plant cycles. One is organic Rankine cycle, and then we extended the organic Rankine cycle to the next version of flash cycle, which we called as organic flash cycle. And now the power plant cycles, advanced power plant cycle has been extended to the one more advanced power plant cycle, which is called as Kalina cycle system. In this Kalina, this chapter is focused on Kalina cycle. What are the main contents of this Kalina cycle in this chapter? Is the first one is I'm going to explain the basic Kalina cycle system, that is essentially with essential components and process. And then I'm extending the presentation to on discussion on thermodynamic properties of binary fluid system, because this Kalina cycle is working on binary fluid system. In earlier cycles, this is single fluid system, that's Rankine cycle, either organic Rankine cycle or organic steam Rankine cycle. But here, this is a Kalina cycle has two fluids are mixed together. That's why it is called as binary fluid system. So, to solve the process and entire Kalina cycle system, the solving of thermodynamic properties are slightly different compared to the single fluid system because of the addition property. One extra property is coming here, which is the concentration. In addition to the pressure and temperature, concentration also we have to deal. That's why especially the thermodynamic properties are focused in this presentation. After finishing the introduction on thermodynamic properties, I'm going to explain the process, thermodynamic process. This process also differs compared to the earlier studied thermodynamic process. For example, in your thermal engineering subject, you might be studied adiabatic process, isentropy process, isenthalpy process, isothermal process, or etc. But the formulation, the solution of those process, thermodynamic process, are completely different compared to the process involved in the binary fluid system. And then after finishing the properties and the process, I'm entering into the cycle, Kalina cycle, where we can apply the knowledge of solving applying the thermodynamic properties and also solving the thermodynamic process to evaluate the Kalina, finally the Kalina cycle, maybe basic level or added with some added components such as regenerator, some distillations like diffling matter, etc. After able to evaluate the Kalina cycle system, we can extend the study to the simulation, the analysis, and optimization of the few parameters such as a strong solution concentration, vapor concentration, and some other parameters, cycle parameters such as the source temperature, sink temperature, and boiler pressure, similar to the organic Rankine cycle. So this evaluation includes the energy analysis using first law of thermodynamics and also exergy analysis using the second law of thermodynamics. So we are extending the this Kalina cycle study up to the level of numerical solutions. So we should be able to apply this formulation to the process and Kalina cycle, and finally we should be able to solve some numerical problems to find the power generation from the Kalina power plant and efficiency like energy efficiency and exergy. The today's class is focused on basic Kalina cycle and also some introduction about the properties I am giving. Why I am giving the introduction about this basic Kalina cycle is because earlier our study is Rankine cycle. So I am selecting all the components in the basic Rankine cycle and few extra components that is essential components, I think so. Yeah, I am explaining the essential components to be used in Kalina cycle. After finishing the study with the essential process and essential components, then we can extend the additional components such as internal heat recovery at lower temperature or internal heat recovery at the higher temperature, and increasing the concentration at the end of the boilers. That's the distillation of the working fluid, etc. We can extend after finishing the study with the basic Kalina cycle system. So in Kalina cycle, when it is invented, Alexander Kalina is invented in 1984. He invented this Kalina cycle, and his name, the inventor name, thermodynamic cycle, has been called as Kalina cycle. First, let me explain the basic configuration of this Kalina cycle system with the essential components. I'm using Blackboard. Just tell me if is it convenient to you or not. Are you able to see the lettering?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. I'm starting with the heat recovery vapor generator because earlier we also has the discussion on heat recovery vapor generator in organic Rankine cycle and organic flash cycle. So first I am focusing on economizer and evaporator, because between evaporator and superheater some additional process are coming. In Rankine cycle there is no any additional process or components, but here Kalina cycle it requires in this what configuration, because we have so many configurations of Kalina cycle. I am explaining very fundamental Kalina cycle which is suitable to the low temperature heat recovery. If the source temperature is increasing, the configuration will change. Let us say medium temperature source, the configuration is Kalina cycle applied to medium temperature source. At higher temperature, configuration is different. Kalina cycle applicable at a higher source temperature. So this is economizer. This is evaporator. So hot gas is coming in the evaporator and economizer in this direction. In opposite direction, working fluid is going. The temperature of the working fluid is increased in the economizer. And in evaporator also, the temperature of the working fluid is increasing because this is the binary fluid system. The phase change takes place at variable temperature. Phase change starts at bubble point temperature and ending at the dew point temperature. But in this Kalina cycle model, before reaching to the dew point temperature, that means the evaporation process is incomplete. If the evaporation process is incomplete, what we can expect? We can't expect 100% vapor. This is not saturated vapor. This is unsaturated vapor. So it consists of liquid and vapor. And this separation process is similar to the flash cycle, but there is a difference between the flash cycle and Kalina cycle. Because in the flash cycle, the separator is used at the end of economizer, but here the separator is used at the end of partial evaporator. Instead of saying complete evaporation, it is a partial evaporation. Now see, the mixture consists of a liquid part and vapor part. Since it is a vacuum mixer, we need vapor only, not the liquid. For power generation, vapor only we required. So this vapor straight away we can supply to the turbine or if somebody wants to raise the working fluid temperature, I think superheat with using the superheater, then one can also use the superheater in the heat recovery vapor generator part. But this is the influence of superheater, whether it is effective, worthy, justifying or not, that we can see in the analysis part. Now see, the vapor alone has been supplied to the superheater. This superheated vapor has been collected and to the turbine. This is the vapor turbine. Kalina cycle, we are using the vapor turbine. I can call this as VT. VT means this is the vapor turbine, where this is connected to the generator for electric generation. So electricity has been generated in this alternator. So the superheated vapor has been supplied to the turbine. The remaining parts are same. That means except this separator, I'm adding this component separator. The separator is, you can't find this separator in a single fluid system, that's organic Rankine cycle. But in binary fluid system, this separator is required to facilitate the separation of liquid part and the vapor part. So at the end of this turbine, what is the next component in the basic power plant? Condenser is the next part, but straight away we can't condense this vapor at the sink temperature, because this vapor consists of more ammonia, because the working fluid is mixture of water and ammonia. So in the separator, the vapor consists of more ammonia. That's why this is almost 90% or 95% of concentration. If X is equal to 0.95, that indicates 95% is ammonia and 5% only water. So straight away, this more quantity of ammonia we can't condense in the water cooled condenser or air cooled condenser. That's why it has to be diluted by adding the water. Since already we have the liquid here almost close to the water concentration, that's why you may call this as weak solution. So corresponding concentration, you may call this as weak solution concentration. XWS is a weak solution concentration. But this liquid is at the high pressure. Since the boiler, the pressure in the boiler is not at the low pressure, this is pumped to the high pressure. That's why the liquid pressure has to be decreased to the low pressure for easy mixing of this vapor, because vapor is at the low pressure, but this liquid is at the high pressure. For that reason, some throttling is required, so that this throttling device is decreasing the liquid pressure from high pressure to the low pressure. See, at the exit of this throttling valve, this liquid is ready to mix with this vapor, so that the concentration of this vapor we can decrease. So there is a mixing process at the exit of the turbine by adding this weak solution. So concentration is decreased here. So concentration is decreased from 95%, approximately from 95% to 30% or 35%, depending upon the concentration of this strong solution. So now this is ready to condense. This is easy to condense this vapor. See, this is a assume this is a complete 100% vapor. This is 100% liquid. The resultant fluid is liquid plus vapor mixture. So now directly you can communicate this fluid to this condenser without any worry, because now we are able to condense this vapor to the saturated liquid form due to lower concentration. This is the condenser. I'm showing the water cooled condenser. We can also use the air cooled condenser depending upon the availability of the water at the local conditions. Now this vapor is completely condensed to the saturated liquid form. This condenser can also be called as absorber. Why it is also called as absorber? Because we are absorbing this vapor at the inlet of this condenser by rejecting heat to the surroundings. So as I told in the earlier introduction of Kalina cycle system, this mixture is geotropic in nature. And the geotropic mixture, these two fluids can be separated by adding heat. See here we are adding the heat in the boiler. We are able to separate the fluid, and also we are able to mix the fluids. Here. Two fluids are mixing by rejecting the heat. The mixing process we are calling as absorption process. The vapor has been absorbed into the liquid part, which is having lower concentration. So its mixing process takes place, that absorption process takes place at the inlet of the condenser. Now this liquid straight away we can send to the boiler after pumping. So pump, what it is doing, it is raising the pressure from the low pressure to the high pressure. That is from the condenser pressure to the boiler pressure. So this is the configuration of this basic Kalina cycle. In this basic Kalina cycle, what I am showing the components is the first one is boiler. I am calling this as the heat recovery vapor generator. After heat recovery vapor generator, then is the turbine and condenser pump. These four components are common with the Rankine cycle. In addition to this Rankine cycle, what are the extra components we are using in this Kalina cycle? The extra components. Extra components are what we are using here. The first one is separator and throttling device. So this separator and throttling valve is extra components, and this is mixer also. Actually, mixer is not the component. This is absorbed at the inlet of the condenser. So this setup is a extra setup compared to the Rankine cycle system. And see the quality of this Kalina cycle compared to the Rankine cycle is, in this heat transfer, see the boiler configuration, the heat has been added in the direction of hot fluid. I am saying this is the hot gas is coming. First it is entering the superheater and then followed to the evaporator and economizer. Therefore, the exit of economizer we are calling this as exhaust gas. If it is hot gas has been used in case of waste heat recovery. So this is providing the heat recovery, the waste heat recovery from the hot gas. So in Rankine cycle, evaporator consists of working fluid is evaporating at the constant temperature. But in this Kalina cycle, since two fluids has been mixed together, the temperature, working fluid temperature is increasing in the evaporator. From starting is bubble point temperature, but this is incompletely stopped to collect the vapor and the liquid. So this is this temperature at the exit of this evaporator is below the dew point temperature of the working fluid at that particular pressure. So I'm using some terminology such as bubble point temperature, dew point temperature, and properties, mixer properties. In the mixer properties, see here, this is the mixer at the end of evaporator. This is a working fluid. This is a mixture of H2O and NH3, and this is also a mixture of liquid and vapor. We are separating. So see, the concentration at the inlet of separator is different. This concentration we are calling as strong solution concentration. See, we are pumping strong solution. Why it is called strong solution? Compared to the weak solution, the concentration of ammonia is more in this solution. That's why it is called as strong solution concentration. Yes, SS means strong solution. WS is a weak solution. In addition to these two concentration, is there any another concentration? One more concentration you can see. This is the vapor concentration. So finally, there are three concentration: the vapor concentration, weak solution concentration, strong solution. These three concentration is controlling the properties of Kalina cycle system. Now let me list out the various process involved in this Kalina cycle system. And the first one is the heat transfer. This heat transfer happens in heat recovery vapor generator. There are three sections in heat recovery vapor generator: economizer, evaporator, and the superheater. After finishing this heat recovery vapor generator, or between the process in the heat recovery vapor generator, that means between evaporator and the superheater, this process, that is the separation, is a one process. The separation process also we have to solve to evaluate this Kalina cycle system. And the expansion process, what type of expansion? We may assume this is a adiabatic expansion if there is no heat transfer to the surroundings, or if some heat is also considered during this expansion. This is the heat transfer with heat rejection. So there are two possibilities of this expansion takes place. We can solve either adiabatic assumption or diabatic assumption. Then after finishing this process, this expansion process, what we have to solve? We have to solve one more process, throttling process. Throttling process also we have to solve to evaluate this Kalina cycle system. Already we studied this throttling process in refrigeration air conditioning subject. Similarly, here enthalpy is constant in this throttling process based on the concept of isenthalpic assumption. The temperature at the exit of this throttling valve or throttling process we can simulate from the thermodynamic process, and also the evolution of the process, thermodynamic process. And then mixing process. Mixing is also one process similar to the opposite to the separation process. In separation process, two fluids has been separated, liquid and the vapor has been separated. In the mixing process, two fluids has been mixed. That's weak solution has been mixed, combined with the vapor, so that you are resulting one more fluid that we are calling as strong solution. So in this mixing process, what we are assuming, before entering into the condenser, that means excluding the absorber, this mixing process is adiabatic mixing process. If we considered or including the absorption process, that's condensation process, the mixer and condenser together, we may call this as a diabatic mixing. Diabatic mixing indicates the mixing of two fluids together, and also followed by heat rejection to the surroundings as per this drawing. So combinedly we can solve this adiabatic mixing with the heat transfer. It may be heat addition or it may be heat rejection. But in the Kalina cycle system, we have to consider heat rejection only to the surroundings for condensation process. So this process is called as the diabatic mixing process. And then pumping, similar to the turbine, the pumping also we can solve to evaluate the Kalina cycle system. So how many processes you can list out here? Heat recovery vapor generator, turbine, the mixing, throttling, separation process, and condensation process, or some combined mixing and absorption process, diabatic mixing process, and pumping. This process we have to evaluate. I am going to explain one by one process, so that after finishing the explanation of this thermodynamic process, so that we can combine or we can club the knowledge of evolution of this process, and finally we can evaluate the Kalina cycle system. So I'm going to explain next topic is properties. And before going to the discussion on thermodynamic properties of this binary fluid system, do you have any doubts on this configuration, this Kalina cycle configuration? I will clarify if you have any doubts in the process configuration, so that it's maybe easy to catch my explanation for properties and also process, thermodynamic process. Okay. At the end of this class, I will interact with you for discussion of this doubts and questions query. See, I want to add one point here. Okay, this is the basic Kalina cycle system. What is the next version of Kalina cycle? Next version means to improve the performance. Some additional components we can use in this Kalina cycle system. What are the possibilities to use the additional components in the basic Kalina cycle system is similar to organic Rankine cycle system. See, at the exit of turbine, the working fluid temperature is not close to the condenser temperature. Since this is also ammonia is also organic fluid, but H2O is not organic fluid. But since I can say the vapor turbine is more in ammonia, that's because of the higher concentration. So the temperature of this working fluid at the exit of turbine is higher than the sink temperature. So there is a possibility to add some regenerator similar to the organic Rankine cycle. This heat can be transferred to the boiler. That means at the inlet of this working fluid, this liquid fluid. So the temperature of this liquid can be increased before entering into the boiler by taking or by recovering the heat at the exit of the turbine. So there is a possibility to include the regenerator, that's internal heat recovery at the exit of this turbine. And second one is, see the separator at the exit of separator in the liquid line, that is a weak solution. The weak solution has to be condensed into the absorber. So this this temperature has to, because this is a high temperature at the exit of this evaporator, the temperature of fluid is very high compared to the sink temperature. But this amount of heat we have to bring down to the sink temperature, even though there is a small drop in temperature in the throttling valve. But we can't expect more temperature drop in throttling valve. This is a small temperature drop will be there. Because of the weak solution. Because if it is a solution is ammonia is more, we can expect some considerable temperature drop. But this is more working fluid is rich with water. That's why we can't expect higher temperature drop. So at the exit of throttling valve, also the temperature of the fluid is considerably high compared to the sink temperature. Therefore, the temperature at the exit of the separator can be brought down to at least close to the sink temperature, slightly above the sink temperature, by rejecting heat to the working fluid. So here also one more possibility to adapt a regenerator at the exit of this separator. So one is we can use at the exit of this turbine. So that can be used, that can be called, maybe at the here also we can use after mixing, instead of adding regenerator at the exit of the turbine, after mixing also we can use. So there are two regenerators here. One is low temperature regenerator. Low temperature regenerator is providing internal heat recovery to raise the working fluid temperature at the inlet of the boiler. Similarly, we can also recover the heat internally. We can recover the heat using this high temperature regenerator. So high temperature regenerator also is possible to recover the heat, so that finally this low temperature regenerator and high temperature regenerator It is helping to improve the efficiency, thermal efficiency of the Kalina cycle system. This is the one of the additional component, that is internal heat recovery is a one additional component in addition to the to be used in basic Kalina cycle for improvement of the performance, that's efficiency. And second, one more point here is the distillation. The distillation is not included here. What is the meaning of this distillation? See the concentration of working fluid at the exit of the separator. This is let me take this is the concentration is 85%. The concentration of working fluid is 85%. What happens? Okay, this 85% of the working fluid is entering into the evaporator turbine. So we are getting a considerable some amount of power generation. But if this concentration is increased, let us say from 85% to 95%, what benefit we can get? So the some benefit means here that is a more amount of NH3 vapor is expanding in the turbine. So that it's completely in constant properties I'm going to explain in the after finishing the cycle. We will get certain benefits like improvement in the performance. So how to increase the concentration of this working fluid, let us say from 85% to 95%. So one component we have to incorporate at the exit of this separator. That component is called as a distiller, or this is also called as this, defligmator. This is also used in refrigeration system. The defligmator means it is removing some water part and it is sending back to the separator. So by rejecting heat to the surroundings. So by providing some cooling effect in the defligmator, the working fluid concentration is increasing at the exit of the separator. In case if this is cycle is meant for refrigeration system, let us say this is a vapor absorption refrigeration cycle, which is operating in the reverse direction. So what happens? The concentration of working fluid is increasing. We can expect more refrigeration effect because of the increase in the concentration. The ammonia content is more in this working fluid in the throttling device in case of the refrigeration cycle. Automatically, the refrigeration effect is increasing. That's why in refrigeration system, the defligmator is a mandatory, the essential component, so that the COP of the refrigeration cycle we can expect more compared to without using this distillation or a defligmator component. But in Kalina cycle system, the role of defligmator, how extent it is helping the Kalina cycle, I am going to explain in the analysis. It has certain positive aspects using this matter in the Kalina cycle. Similarly, some disadvantages also we can observe using this matter in the Kalina cycle. That I am going to explain in the coming analysis part of the Kalina cycle system. Okay, I am switching to the thermodynamic properties of this binary fluid system. So in the basic Kalina cycle, I explained the fundamental process and components used. And also, in addition to this basic Kalina cycle configuration, what are the possible changes or possible additions to the basic Kalina cycle to improve the performance, maybe the power generation in case of the power plant, or thermal efficiency by supporting the boiler and also by supporting the condenser, adding the high temperature regenerator and the low temperature regenerator. And properties, see the thermodynamic properties. Ammonia water mixer. In this thermodynamic properties, first I am drawing the chart, property chart, temperature, temperature and concentration chart. I'm taking x-axis is the concentration. You know meaning of concentration. If it is concentration is expressed in mass, a mass of ammonia and total mass. This is also can be expressed in molar base. Molar base means the mass is expressed in kg moles. But in SI units, I am expressing this concentration in mass base. That's kg per kg. Kg of ammonia per kg of mixture. That's why it is since it is a kg ratio. It is a number. Concentration is a number. We can change the concentration from 0 to 1. The concentration 0 indicates it's completely 100% water. But there is no any ammonia in the x is equal to 0. And x is equal to 1 indicates this is a 100% ammonia. That means there is no any water. So the properties are changing between water properties and ammonia properties. So let me take the y-axis as the temperature. This is the temperature, T is the temperature, either degree centigrade or Kelvin. I'm closing the chart. I'm drawing a loop, one particular loop. You might be studied these properties in refrigeration subject, especially for vapor absorption refrigeration, VAR system. I consider one pressure and one particular pressure, maybe boiler pressure or condenser pressure. The pressure is constant. In this pressure is constant, how to deal the properties. See, this is I'm showing one region below the saturation liquid curve. This is the saturated liquid. This is a saturated vapor curve. So below the saturated liquid curve, this is a compressed liquid, or you may call this as subcooled liquid. This is a subcooled liquid part, and what we are calling this is a superheated vapor. This is the vapor portion. This is the liquid portion, and this is the vapor portion. And this is unsaturated, but this line, the liquid on this line, saturated line is the saturated liquid. Generally, we will assume at the end of condenser or absorber. This is also saturated vapor, and between the saturated liquid and saturated vapor, what is the status of working fluid? This is the wet mixture. The wet mixture consists of liquid part and vapor part. Let me draw a isotherm. Isotherm means this is a temperature is constant. For example, the mixture is here. We are showing the state of the working fluid at this particular point. In this particular point, this consists of liquid and vapor. We can apply the lever rule. In metallurgy, we might be applied this lever rule to find the carbon content in iron carbon diagram. That is ferrous and carbon mixture. So similarly here, this is a mixture. If the mixture is separated to liquid and the vapor, what I explained in earlier Kalina cycle system, this is a saturated liquid and this is a saturated vapor. The fluid consists of a concentration. Let me take this is at the inlet of the separator. Concentration is the strong solution concentration. The strong solution concentration has been separated to the weak solution concentration and the vapor concentration. So this is we are calling as X, and this is XL. L stands for liquid, and this is XV. V stands for the vapor. So in the mixer region between the saturated liquid and the saturated vapor, the working fluid has three concentrations. One is the concentration at that particularly at the directly at that state, that is a strong solution concentration, and this concentration at this mixer also has the concentration at the liquid part, saturated liquid part, and also concentration at the saturated vapor part. You may ask how to solve these points, that is a liquid state and the vapor state. This can be solved using the enthalpy chart. Not only the temperature, similar to the temperature chart, the enthalpy charts also available. In the enthalpy charts, it's easy to evaluate the mixer using this lever chart, because enthalpy charts consist of one more extra curve which is called as auxiliary curve. That auxiliary curve supports the saturated liquid and saturated vapor, so that we can solve the mixer properties using graphical solution. Let me draw one more line, the vertical line here. Assume this is the vertical line. So assume this is a heating process. Some heat has been added. What happens once we are heating at concentration is constant, the mixture concentration is constant, the temperature of the fluid is increasing. Let us say we are here, the working fluid temperature is increasing, and it is initially it is subcooled temperature. So the temperature is increasing and reaching to the saturated liquid state. Assume this is the economizer in case of the boiler. Okay, in boiler, what is happening? The temperature of the working fluid is increasing. At the end of economizer, the working fluid temperature is reached to the saturation temperature. Okay, we entered into the next is evaporator. In evaporator, what is happening? I am showing the complete evaporation process in this property chart. In evaporation, what is happening? If it is a single fluid system, there is no such loop. Only one line will be there. So the saturation at this saturation, the boiling starts at this saturation temperature. So this temperature you may call this or this entire curve we can call this as saturation line, bubble point line. We may call this as a bubble point line. This may be called as a dew point line. So here what is happening, the saturation, once it is touching the saturated liquid part, the phase change takes place. So phase change starts at the bubble point temperature, BPT, and phase change is ending with the dew point temperature. So bubble point temperature to dew point temperature, this component we are calling as evaporator in Kalina cycle system. After crossing this dew point temperature, the temperature continuously it is increasing, starting from beginning to ending. This is superheated vapor. The temperature is continuously increasing, but here there is no phase change. In superheater, there is no phase change. The temperature of the working fluid is increasing with the sensible heat addition. In the economizer, there is a sensible heat addition, and superheater also in a sensible heat addition. But in the evaporator, the heat addition is a latent heat addition. In what I explained in basic Kalina cycle, the evaporation is incomplete. Let me select one state between the liquid and the vapor. Yes, at this state, what we are doing, the evaporation is completed. So we can separate the liquid and the vapor. Now, at the exit of this evaporator, we can separate the liquid and the vapor. Now you may see this is the liquid part and this is the vapor part. But the temperature is constant. Here the temperature is constant. You may say this is the boiler temperature or the separator temperature. Separation takes place at the constant temperature process, the liquid part and vapor part. You may see how mass can be calculated as per the lever rule. See this length, that means the liquid to state, this length is directly proportional to the vapor mass. and this length, that is the state to the vapor, this length is directly proportional to the liquid mass, opposite direction. I'm saying the opposite direction as per the lever rule. This length is proportional to the vapor mass, and this length is proportional to the liquid mass as per the lever rule. So not only mass ratio, not only this mass ratio, and enthalpy ratio also. That means HV minus H and HL. If it is enthalpy, I'm going to show in the next slide. There's enthalpy chart. This is HL and this is HV and this is H is a mixture. Enthalpy is also following this lever rule. And concentration is also following the lever rule. That's HVX, HVX, and HL. These are also following the lever rule. So lever rule is helping to find the unknown mass and to find the unknown enthalpy, and also similar to the unknown concentration. Okay, to find the properties, first we how to solve these properties. So first, assume I am giving the data, pressure, temperature, and concentration has been supplied. Pressure, temperature, and concentration has been supplied. Because the properties, thermodynamic properties is a function of pressure, temperature, and concentration. In single fluid system, the concentration is not necessary. By using the pressure and temperature straight away, we can calculate the properties. But in the binary fluid system, in addition to the pressure and temperature, concentration is required. During the phase change, single fluid system, either pressure or temperature is enough, because there is a relation between the saturation pressure and saturation temperature. That's why no need to supply the both the saturation pressure and saturation temperature in case of the single fluid system. In binary fluid system, the concentration is mandatory even though phase change takes place, because during phase change, just now we saw during the mixer, the concentration is changing for liquid, separated liquid, and also separated vapor. I'm showing one loop here and one particular constant pressure. If x is equal 0, indicate this is the saturation temperature of, this is the saturation temperature of water. X is equal to 1, this indicates the saturation temperature of ammonia. So the saturation temperature is changing at this pressure. I am saying at this pressure, the saturation temperature is changing between the saturation temperature of water and saturation temperature of ammonia. So as per our requirement, for example, we are designing a Kalina cycle. As per our design, for example, I want a particular temperature exactly between the saturation temperature of water and saturation temperature of ammonia. Accordingly, we can control the concentration. So accordingly, we can control the concentration. As per the concentration, we can control the saturation temperature of the mixers from the bubble point temperature to a dew point temperature. So finally, what is happens here? The concentration plays an important role in deciding the performance of the Kalina cycle. The first region, I listed out 5 regions in the earlier drawing. And the first region, we may call this as if the temperature is equal to the bubble point temperature. The temperature is equal to the bubble point temperature. What is the name of this fluid? See, refer this drawing. If the temperature is equal to the bubble point, this is the bubble point temperature line. What is the name of the region? What is the name of the region out of 5 regions? This is a subcooled liquid, and this is the saturated liquid. This is also liquid, but this is the difference between this liquid and this liquid. This is subcooled and unsaturated liquid, and this is saturated liquid. And this is the liquid plus vapor. This is the saturated vapor and superheated vapor. So how many regions I am showing here? 1, 2, 3, 4, 5 regions I am listed here. These 5 regions are listed and they are decided or defined based on the given pressure, temperature and concentration. So I am giving randomly, I am giving one pressure, temperature and concentration. How to decide whether the state is region 1, region 2, region 3, region 4 or region 5? We have to compare the bubble point temperature and dew point temperature. That's why first what we have to do, we have to calculate the bubble point temperature. How to find the bubble point temperature? Bubble point temperature can be calculated at given pressure and concentration. The concentration, for example, here this is the x lines. X means concentration lines. The concentration line and pressure is both are intersecting each other. It is giving the this is giving the temperature. So the bubble point temperature can be calculated from the given pressure and the concentration. Similarly, the dew point temperature also can be calculated. Dew point temperature also can be calculated from the given pressure and the concentration. But this concentration, we may call this is instead of saying x, this is the y. X is the concentration in the liquid part, and y is the concentration at the vapor part. So this we are calling as x is used to find the bubble point temperature. Y is used to find the dew point temperature. So we can calculate. There's equations are available to find y is a function of x. So from given pressure and concentration, we can calculate the bubble point temperature as well as dew point temperature. So if temperature is equal to the bubble point temperature, the region is called as a saturated liquid. And second, if the temperature is less than bubble point temperature, the temperature is less than bubble point temperature, what is the region? So this is less than the bubble point temperature. What is the region? Name of the region. This is unsaturated liquid or compressed liquid. I'm calling this here is subcooled. I'm using refrigeration terminology. Subcooled liquid. And third case, if T is equal to dew point temperature. What is the name of the fluid? Yes, if the temperature is equal to this dew point temperature, the fluid is equal to saturated vapor. Fourth one, if the temperature is greater than bubble point temperature and the temperature is less than dew point temperature, what is the name of the region? The temperature is between bubble point temperature and dew point temperature. That region we just now we discussed, that is a mixture, the liquid vapor mixture. The last one, the temperature is greater than dew point temperature. This region is called as superheated vapor. So at given conditions, that is the pressure, temperature and concentration, we may decide the state may fall any one of these five regions. I am listing 5 regions. Out of these 5 regions, the state will decide only one region. One region only it is falling. The first we have to identify that region. Once you are able to identify that region, and we can directly collect the properties at particular region. For example, the given pressure, temperature, and concentration is showing the working fluid is saturated liquid. Straight away, we can refer the saturated liquid properties, that is saturation properties. At this saturation properties, we can pick the properties. What are the properties required? Let us say enthalpy, entropy, etc. If the enthalpy and entropy is available, exergy straight away we can calculate, or if we tables are available for exergy, or without calculating exergy from given enthalpy and entropy, straight away we can pick the exergy values for second law analysis. I'm adding one more property chart and then I will finish. Enthalpy concentration chart. The y-axis, instead of selecting temperature, now I selected enthalpy. X-axis is same, that's concentration. I'm drawing one loop here and one more curve. See, in the earlier drawing temperature concentration chart, only two curves I draw. One is for liquid and another is for the vapor. Now, in addition to the liquid line and vapor line, there is one more extra curve is there. This is a saturated liquid and this is a saturated vapor. And between the saturated liquid and saturated vapor, this is a liquid plus vapor region. And this is the subcooled liquid and this is the superheated vapor. This is the saturated vapor, this is saturated liquid. Now see what is why extra one more extra curve is given. This is called as auxiliary curve. The auxiliary curve is supporting to evaluate the properties in the liquid plus vapor mixture. That is, if the temperature is between the dew point temperature and bubble point temperature, then we can take the support of auxiliary curves so that we can evaluate the properties of liquid and properties of vapor from the given properties of the mixture. For example, let me select one state here. Yeah, this is the state of the mixture. How to solve the state of the mixture using lever rule? So I don't know the concentration of the liquid because I know the concentration of the working fluid. Let me take, this is the concentration of the mixture. This concentration of the mixture, once it is separated, it has liquid concentration and vapor concentration separately. At what condition I separated at the constant temperature isotherm? I had to develop the isotherm, but since I don't know the concentration of the liquid, some iteration method is required. This is a graphical graph I'm explaining now. This is a graphical solution to solve the process at the liquid and vapor mixture. So let me assume one concentration, arbitrary, I am taking one concentration for the liquid. This liquid concentration, after selecting this liquid concentration, draw a vertical line. The vertical line has been drawn here up to the auxiliary curve. After touching this auxiliary curve, draw a horizontal line. A horizontal line has been drawn here. And combine the initial state, that is the starting point, and this ending point. How to combine? We can take the scale and pencil and combine these 2 points. Combine these 2 points, what we can get? We can get a isotherm. This is the temperature is constant. The liquid concentration, liquid is at this temperature and vapor is also at this temperature. All the state points are showing the constant temperature states, but our selected state is not falling on this line. So our initial assumption is wrong. So how to refine this iteration? The second iteration, we have to select one more concentration, appropriate concentration, because we, since it is moving, this is state is above this line, we have to take extra concentration, additional more concentration compared to the earlier assumption. Now I'm drawing one more triangle. See, this is the starting point and this is the ending point, and joining this starting point and ending point, it may uh, go through the state point, or maybe small error, it's coming a small error. To refine this iteration, again we have to select the appropriate concentration, still matching the consistency. This process can be repeated for to solve the final temperature. Assume in the second iteration I got the answer. That means this line is passing through the state. What I can see, my results are showing this is the final temperature. This is the final temperature. What at given pressure and concentration, at given pressure and concentration, this is the state we are able to show the state, and this is the temperature. Temperature is resulted through this iteration process, and this is a resulted liquid concentration, and this is the resulted vapor concentration. So using this auxiliary curve, by supporting this auxiliary curve, it is easy to solve the mixture properties using the iteration method. This is saturated liquid line and this is the saturated vapor line. Enthalpy shows the difference between the enthalpy, that is the liquid and vapor. What is the difference between the enthalpies of vapor and enthalpy of liquid? This is the latent heat. Since it is at x is equal to 0, this is latent heat of water at this pressure, and this is the latent heat of ammonia. At the same pressure at x is equal to 1. So between x is equal to 0 and x is equal to 1, the latent heat of mixture is changing from the latent heat of water to the latent heat of the ammonia. That depends upon the concentration, mixture concentration. For example, it may be x is equal to 50, the 50% is the water and 50% of the ammonia, or x may be less than 50% or x may be more than 50%. Depending upon the concentration, we can evaluate the enthalpy. Now see here, coming to enthalpy, I am showing XL, X and XV. For this state, it consists of enthalpy of liquid, and this line I am showing. This is it shows the enthalpy of the vapor, and this shows the enthalpy of the mixture. So XV, X and XL follows the lever rule, and similarly XL, X and XV also following the lever rule. And mass also, see the mass of the mixture, mass of the liquid, mass of the vapor. And this is the enthalpy of the mixture, enthalpy of the liquid, enthalpy of the vapor. Concentration of the mixture, concentration of the liquid, concentration of the vapor. All are following the lever rule. The lever rule, here I am showing the lever rule. This is the length towards the liquid line. This is the length shows towards the vapor line. So this length is directly proportional to the vapor properties, maybe enthalpy, concentration, or the mass. And this opposite length means, yeah, this length, vapor side length, is directly proportional to the properties of the liquid. So we can easily evaluate the properties of enthalpy, that's mixture, or individual properties such as liquid and vapor by applying the lever rule. I'm going to explain the formulation that's applying the lever rule and the mass balance, energy balance, and exergy balance in case of the second law of thermodynamics in subsequent thermodynamic process. Because today I just outlined the reading of thermodynamic properties for the binary fluid system. With this information of this binary fluid system, I'm going to explain the solutions for various thermodynamic process in the Kalina cycle system. And those are separation process. This is almost looking like a separation process, how to solve the separation process. In opposite direction, I can say this is a liquid and vapor is mixed to a mixer, then that is called as adiabatic mixing process. If some heat transfer takes place, maybe heat addition or heat rejection, that becomes the adiabatic process. So the same state is showing here. For example, one particular state, this is one state. State is having concentration is X and having enthalpy is H. Before throttling, this is the state, and after throttling also same state. I'm showing, let us say H1 is equal to H2, X1 is equal to X2. For throttling process, we can't show any process line because the initial state point and final point both are same in this throttling process. In that particular case, how to evaluate the exit temperature? Even though enthalpy and concentration is same, but pressure is different. This is a the P1 is greater than P2 with the reference of differential pressure during this expansion process, throttling process. We can evaluate the temperature T2 because T2 is less than T1 after this expansion. So I'm going to explain all the process, including distillation process in Kalina cycle system, with the help of the charts, the graphical solution, as well as also from the tables, the particular values, the analytical solutions. So the next class, I'm going to explain the solutions for various. I'm going to discuss the solutions for various thermodynamic process, and by framing the formulation for energy and also exergy.